good morning or good afternoon, whatever time it happens to be. I'm Tuomo Kauronne, the president of Arbonaut Limited, and I will today present to you the ways that Arbonaut, which is a forest technology company based in Joensuu, Finland, collaborates with universities and research institutes all around the world. Arbonaut is very much a research partner. We were founded up like a startup company of the University of Eastern Finland and have always maintained close relationship with research and also contributing and collaborating with student education, especially in forestry, geoinformatics, and also mathematics and computer science. Arbonaut's main business is geographic information systems, especially forest information systems. We conduct forest inventory based on airborne laser scanning, satellite imagery, and field campaigns. Then we do geospatial modeling, works, for example, on railroads and power lines. And an important and the fastest growing activity is REDD+ and other climate agreement, especially the Paris Climate Agreement related services that emphasize sustainable forestry and carbon capture in especially tropical and subtropical forests all around the world. In this map, you can see Arbonaut's forest and climate activities and their current geographic extent. So we operate on 6 continents in roughly 30 countries in Europe, Asia, Africa, South and North America. We still haven't had a project in Antarctica since no trees have been found there. But I have always made this promise that if that tree is discovered, I will definitely arrange for that to be measured. Arbonaut was founded in 1994 by myself and my contributor, collaborator Pertti Jyrkönen. We currently have roughly 60 staff from 20 countries, a turnover about 2.5 million euro annually, and we have permanent offices in Joensuu and Helsinki, both in Finland. But in practice, with these many projects, much of the staff works part of the time in the target areas all over the world. In addition to working with universities and research institutes, our close partners include NGOs like the World Wildlife Fund, International Union Conservation Network, Oxfam, and others who also normally have global operations. Regarding collaboration between Arbonaut and universities, it follows following patterns which I think can be instructive for many of the other partners and universities partnering with companies likewise. So Arbonaut's business is based on research that is first conducted at universities in joint project and then commercialized by Arbonaut. Very few companies, and Arbonaut is no exception, can actually afford their own research initiatives. And the more uncertain the outcome of the research, the more necessary it is to partner with good research partners who first find out what works, and then Arbonaut hopefully will be able to build a product or a service based on that will help then a wide range of customers. So the principal forms of collaboration we have conducted are joint applications for research financing, both to national authorities, to the European Union financing like the Horizon program, and they often require, in fact, university and private sector partnerships. We engage in supervision of Master of Science and PhD students at both levels, and then we also carry on joint research efforts and produce research articles where Arbonaut often provides the material and then the university team conducts analysis on that material. Given the vast range of remote sensing and field measurements we have conducted, we can often provide much wider and much bigger sets of raw material, raw data for algorithmic and other type of remote sensing research. We provide internships for master students. In fact, every year, between 5 and 10 master students or bachelor students sometimes arrive at Arbonaut. And then in some cases we also provide part-time work for such students to allow them to finance their studies. In this collaboration, the roles are rather clear. So universities get the benefit of publications and degrees, and Arbonaut then often recruits some of the graduates already during their study and provides materials, tools, and supervision. Some of the principal collaborating universities, in Arbonaut's case, are University of Eastern Finland, School of Forestry and Department of Computer Science and Mathematics, all based here in Joensuu, so close to us. Then Lappeenranta and Lahti University of Technology, or LUT, especially Lappeenranta School of Engineering Science, where I personally was working as an associate professor of applied mathematics for 17 years. There's a lot of collaboration with University of Helsinki School of Forestry, Department of Geography and Department of Mathematics, both in algorithmics research and also in providing applied projects for students. Outside Finland, one of the longer-standing collaborators is Perm University in Russia, with whom we collaborate on forest inventory, especially based on airborne laser scanning, as applied in Russia. And then among research institutes, ones which are closest to our domain of application and certainly physical proximity also helps. Luke, the Finnish Natural Resources Research Center, Syke, which is the Finnish Environment Center, especially focusing on water bodies, University of Turku Department of Geography, State Technical Development Center, VTT, Space Technology, these are all in Finland. And then among the international collaborators, University of Hamburg, Geoinformatics is a close affiliate, Sokoine University of Agriculture in Tanzania, University Putra Malaysia, UPM, in Malaysia, Kuala Lumpur, and also Chinese Academy of Science, the Institute of Natural Resources Research. I will then outline briefly to you some concrete examples of fruits of such collaboration, and I've selected 3 different cases that illustrate maybe the most successful and longest-standing modes of collaboration that we've had. So the first one resulted in Finland, actually so far as the only country in the world, adopting airborne laser scanning, or LiDAR, as the only operational forest inventory method in the whole country. And this is largely a result of work with the University of Eastern Finland and Arbonaut, and later on also 2 other companies, Teratech and Blom, which are both based in Norway. Then another case, we have developed a novel machine learning method for forest inventory together with the Lappeenranta University of Technology and Arbonaut, and that is now applied, for example, in these climate-related forest inventory cases with satellite data. And finally, trials of LiDAR inventory in Russia between Perm University and Arbonaut. So let's start from the first one, of making airborne LiDAR the main operational inventory method in Finland, something that took about 15 years altogether. Airborne laser scanning, or LiDAR, is a technology that provides 3-dimensional information on forest structure. Here in the screen you see aircraft flying at roughly 2 kilometers of height and covering a swath of roughly 1 kilometer in diameter that provides a 3-dimensional point cloud that describes the structure of the forest canopy. And as you can see in the picture, a laser beam, and there are about 100,000 laser pulses sent every second, is reflected both from the top of the canopy, from the branches, and finally from the ground. And the statistical profile of these returns allows us to use mathematical modeling and Bayesian statistics to correlate this statistics with the kind of trees and kind of forest which are beneath the aircraft. And it's particularly useful in determining the height of the trees, which is not attainable by most other methods. ArboLiDAR is Arbonaut's operational platform based on these algorithms and it is a Bayesian statistical package that takes aerial imagery for tree species recognition, airborne LiDAR for height and shrub density recognition, and finally calibrates these with field measurements on sample plots, the volume, to estimate things like timber volume, biomass, stem number, other parameters that are important for characterizing both natural and planted forests. And all this in the middle takes place in an n-dimensional feature space, a mathematical entity where Algorand's algorithms do their work. We have conducted forest inventory based on these principles in roughly 1 million hectares in Finland by now, several million hectares, and then in about 10-15 different locations elsewhere in the world wherever LiDAR data has been available, ranging from a few thousand hectares up to 2 million hectares per campaign. Then another derivative of research, so that previous research was particularly conducted between the University of Eastern Finland School of Forestry and Arbonaut in this next stage, this between Lappeenranta University of Technology and Arbonaut, and it's about the mathematical methods when we need to combine airborne laser scanning with satellite images. And this is the case in most parts of the world, especially when large areas of forest need to be monitored for their carbon capture potential, according to the Paris Climate Agreement and the RED Plus program of the United Nations. So here, one of the challenges is how do we use the limited resources of LiDAR that we have available. So in this case, the area we developed this in was in southern Nepal, an area known as Terai Arc Landscape, or TAL, which is on the border area between India and Nepal. The area altogether has about 2 million hectares of forest, but we had resources to capture only about 100,000 hectares of that on LiDAR, and then wanted to build a model based on satellite images that uses these LiDAR blocks for calibration. So the sampling technique developed for finding these blocks and how to use the forest information obtained from those using ArboLiDAR was a development we did together at Lappeenranta University of Technology. And here you see the result of a random allocation of 5,000 hectare LiDAR blocks that were flown, and then that gave us on the order of 10,000 different virtual sample plots or surrogate sample plots that could be used to train very accurately a satellite image-based model. And that was then applied to the whole area. This whole mathematical stack or statistical stack needs to be unbiased. So for that reason, the careful selection of the algorithms by which these samples of both sample plots and those LiDAR blocks are made is challenging, but can be proven to satisfy those statistical results. Field sample plots are only collected under those areas that are covered by LiDAR. So in addition to this 20 LiDAR blocks, we had 738 field sample plots that were regular clustered samples within those 5 by 10 kilometer LiDAR blocks. So altogether, a nice mixture of traditional forest inventory and applied mathematics. This LiDAR block sampling was done like a weighted sampling exercise where we wanted to give higher weight to blocks which contain rare ecosystem or rare ecotypes, such as riverine forest or mixed forest. In this part of Nepal, the forest is dominated by sal, Shorea robusta, and in order to have a sufficient sample of also the less common types of forest, we had to use weighted sampling in order to choose LiDAR blocks in areas where other forest types are prevalent as well. Obviously, in this estimation algorithm, those weights have to be inverted so as to get an unbiased outcome of the whole estimate in the end. Then my third example is LiDAR inventory in Russia, a collaboration between Perm University and Argonaut. So here, LiDAR is actually not one of those formally accepted forest inventory methods in Russia, but given the extensive, really vast forest resources of the country, it has deemed to be important to try it out. How would it work? And as a starting point, we took the Finnish LiDAR inventory methods that have been operationally applied, and then they were studied in the Solikamsk forest district, which is in the area of Perm, that covered roughly 10,000 hectares. Here we had no chance of using airborne imagery, so instead we were using satellite imagery, in particular Spot 5 satellite imagery for species recognition. And as a result of these estimates, species-wise precision estimates of the various forest parameters such as timber volume, basal area, number of stems, tree height and tree diameter were obtained. And by and large, as can be seen in these figures, they were roughly of the same order, only slightly less accurate than the estimates in Finland. So as a result, it was concluded that LiDAR forest inventory should be applicable also in Russian harvestable forests. Then Argonaut is just a wide sample of other types of projects where often research institutes are also partnering with us. Training on GIS, we often do that together with local universities, in this case Sokoine University of Agriculture in Tanzania. We have also worked with RD University and University of Dar es Salaam over there. In Nepal, our closest partners often have been the World Wildlife Fund, Nepal, also in the development of this LAMP methodology that was presented. In the case of bioenergy estimates in India and Poland, we were working with Luke researchers and Lappeenranta University once again. And then in the case of Kenya and Ghana, we conducted LiDAR-based model inventory together with Japanese research partners and the local forest commissions as providers of the data and of the target of what to do. So overall, Argonaut couldn't exist without research partners, and we even see it like our mission to make research have a positive impact on the world in terms of mitigating climate change and providing sustainable practices for how to deal with forests. So whether conserving them, whether making limited or combined use of them, or whether harvesting plantations, all that should be done so that it's as positive as possible from the climate and also social sustainability point of view. And for maintaining this, the contacts to research and to contact to local partners, local stakeholders in the forests is absolutely necessary. I thank you for your attention and will be very happy later on to solicit questions should there be an opportunity for that. Thank you very much.